Hello, everyone. My name is Ryong Kim from the University of Texas at Dallas. I'm going to present thermal masking when the illusion takes over the real. This work was done by Haokun Wang, Yatharth Singhal, Hyunjae and myself. So we'd like to start with the definition of thermal masking. We found very interesting phenomenon that when we simultaneously activate the tactile actuator and the thermal actuator together, people actually feel the thermal sensation at the tactile location. By integrating the vibrotactile actuator and the thermal actuator together, thermal sensations could be felt at the tactile location, not at the original thermal location. Thermal masking is a newly discovered phenomenon that shows masking properties through tactile and thermal integration. We found that thermal illusion could be perceived only at the tactile location, dominating the original thermal sensation. And that means the illusory thermal sensation can dominate the real thermal sensation. In thermal masking, we defined 4 different referral states. The first one is no referral state, meaning that people perceive the thermal sensation at the thermal actuator location. The next one is a weak referral state. The thermal sensation could be felt at both the thermal actuator location as well as tactile actuator location, but with stronger thermal sensation at the thermal actuator location, meaning that it's weakly referred. Strong referral. The thermal sensation could be felt at both thermal and tactile locations, but people perceive stronger thermal sensation at the tactile actuator location. And masking. The thermal sensation was perceived only at the tactile actuator location, but the thermal sensation was not perceived at the thermal actuator location. We conducted 3 user studies to explore the effects of thermal masking on various conditions. We used one thermal actuator with 1 or more number of tactile actuators and placed them on the forearm. In each trial, we asked the participants to answer whether they felt the thermal sensation at each location and asked them to draw the perceived thermal sensations on the tablet. Study 1, thermal masking on temperature. We wanted to know if there are any effects of the thermal masking based on different temperatures. We placed the thermal actuator in the middle of the forearm and placed the tactile actuator 8 centimeters apart from the thermal actuator. We then simultaneously activate the thermal and tactile actuators with 4 different temperature conditions: cold with -8 degrees Celsius, cold condition with -5 degrees Celsius, warm condition with +3 degrees Celsius, and the hot condition with +6 degrees Celsius. And here, the temperatures are the plus-minus differences of each participant's skin temperature. We found that the thermal referral occurred at a very high rate at the warm temperature, followed by hot temperature. We also could see that referrals occurred in cool and cold temperatures as well. In terms of referral states, masking was the highest at warm temperatures, followed by strong, weak, and no referral states. In hot temperatures, strong referral showed the highest, followed by masking states. In cool and cold temperatures, all four states were similarly observed. This diagram shows the perceived thermal distribution. We show that there were apparent thermal masking effects in all four temperature conditions. Study 2, thermal masking on distance. The research question that we wanted to know is how far the thermal masking can be observed in our body parts. So we used one thermal actuator and 4 tactile actuators to be placed in different locations apart from the thermal actuator. We chose 4 centimeter, 8 centimeter, 16 centimeter, and 24 centimeter apart from the thermal actuator. And for the temperature condition, we chose warm and cold temperature levels. In warm conditions, 16 centimeters show the highest occurrence rate, followed by 24 centimeter. In cold conditions, 8 centimeters show the highest, followed by 16 centimeters. Now let's look at the referral states. In warm conditions, masking showed the highest in 8 centimeter, 16 centimeter, and 24 centimeter, followed by a strong referral state. At 4 centimeter, no referral state was observed at the highest occurrence rate, followed by masking. In cold conditions, the no referral state showed the highest occurrence rate in all 4 distance conditions, but other states were also observed in different distance conditions. Strong masking effects were observed with various distances in warm conditions, even in 16 and 24 centimeter apart from the original thermal sensation. In cold conditions, thermal masking effects were also observed, but the distribution was not significant. Study 3, thermal masking on the opposite skin side. The question that we wanted to know was whether thermal masking effects could reach the opposite skin side. We placed the thermal actuator at the same location, which is the center of the forearm, and then we placed the 3 tactile actuators on the opposite side of the forearm. We used the same 2 temperatures, cool and warm conditions. We found that the wrist location showed the highest referral occurrence rate in both cool and warm conditions. Occurrence rates were significantly higher with warm conditions. In terms of referral states, the highest occurrence rates were masking states on -8 and 16 centimeter for the warm condition. For the cold condition, no referral states was observed the most in all 3 distances. The perceived thermal distribution showed a clear masking effects on the opposite skin side for the warm condition. We could also see the thermal masking effects on the opposite skin side for the cool condition, but the effect was not that clear. Now, let's talk about why our discovery of thermal masking is important. One of the contributions of our work is the new discovery of the masking phenomenon in thermal sensory cues. Sensory masking has been extensively investigated in other sensory modalities like auditory, tactile, and visual stimuli. But the discovery of the masking phenomenon in thermal feedback is new. We are the first to find the masking effects in thermal stimuli. We also showed the new aspects of sensory masking. We showed that the illusion of thermal sensation could dominate the existence of the original thermal sensation perceiving the thermal sensations only at the tactile location. We also demonstrated that the thermal stimulus can dominate another thermal stimulus at two different body locations. And also, we show that the thermal masking demonstrate the non-uniform thermal redistribution, which contradicts with the existing thermal referral theory. Another contribution of this work is the benefits of engineering. Our findings can impact the various thermal user interfaces and thermal displays with a simple setup. We can strategically locate the vibrotactile actuators with a smaller number of thermal actuators to design a large-scale thermal interfaces and displays, such as gloves, vests, suits, sleeves, and shoes for various VR applications. We can simplify the engineering complexity that thermal actuators have bulky designs with high power consumptions. And finally, we can show the various thermal effects by combining it with vibrotactile cues. So we introduced a new phenomenon called thermal masking, that the thermal illusion can dominate the original thermal sensations, perceiving only the thermal illusion at the tactile location. We clearly observed the thermal masking and other referral states in various conditions, including different temperatures, distances, and even opposite skin sides. We believe that our findings of thermal masking can accelerate the scientific discoveries in human thermal perception. We also believe our findings can contribute to various engineering hardware and human-computer interfaces. Thank you for listening to my talk.